We're going to start off by recapping some of the ideas from the beginning of the class and what we've done so far in Physics 131. So far we've studied kinematics. That's what exam 1 was over. And this was the study of how things move. So we're just looking at motion in this case, but we have no cause or mechanism for how they move or why they're moving. We only know the path that they're taking or the trajectories of the motion. What we've been doing lately and what will be on exam 2 is dynamics. In dynamics, we actually think about why things move. We've been looking at forces that cause that motion, and those forces are that mechanism that we were lacking in kinematics. So of course, you're going to need to still know how things move kinematics, apply them to the dynamic processes and the dynamic forces that we have now under the dynamics study that we're studying now. For all of these different cases, we basically assume that the thing that's moving or being forced is kind of just an object, and it kind of moves as a point-like particle. When we're thinking about how things moving, what is moving? What if not all of it kind of moved together? We need to think about the shape of the molecule and how that might affect the motion. Same thing for dynamics. Where does the force act? What if I push the box not in the middle of the box but on the edge? So what we're going to talk about today are some of these types of concepts. So let's start with a thought question. So how would the trajectory, which is the shape of the motion, so we're talking about kinematics, how would the trajectory of an object change if the shape was a long rectangle? So most of the time we think about a basketball going through the air, but what if instead we threw a book in the air, which is a rectangle? How would the shape of that change? You can actually do this at home. You can throw a book. Don't throw it hard at anyone. Hopefully it's a light book. You can throw your cell phone, which is an elongated rectangle usually. Again, make sure you catch it, and I don't want to have to pay for anyone's cell phone damages. And you can look at what shape the object makes as it goes through the air, and it usually looks like this. In this case, the object, we're not having it change its orientation at all. It's just going to stay the way that it is in the same orientation as it goes through the whole process. And what we find is it pretty much does the same thing. It's still a parabola trajectory like you would have if you had a basketball. So why is this the case? What's going on? So it looks like the shape doesn't change the motion that the object goes through. So for any shape, the overall trajectory is unaffected. The object moves like it's a point particle. But where is that particle located? The location of the particle what it's moving is the center of mass of the object. So the object can be any shape, and the location that's moving as if it's a point particle is a location that we call the center of mass. And we're going to talk more about that later. And so this is just showing you the same thing again. We can identify the center of mass of many objects quite easily. So for instance, for this rectangle that we had moving, you can see that the red dots are now indicating the center of mass, and that center of mass is what's making the parabola. Here's another thought question. If I stand on a scale and I don't like the weight it reports, can I decrease that weight by hanging my leg off the side, like in this picture? So sorry for the terrible illustration, but I did draw these myself. You should do this experiment at home if you have a scale, or at the gym sometime, and see what you get. But in the meantime, or if you've ever tried it before, you know that no, the scale will still report the same weight, which is still mass times grams. And the question is why? How is it possible that all the force is still going down? And so again, just like when we saw for kinematics, for dynamics, the location of the force that's acting, in this case on the scale, is still directly over the scale, even though my leg is hanging off. The majority of the force is coming from my center of mass, the middle of my body. And so we can think of another example. This is similar to the first problem that was on the worksheet on Wednesday of last week. You can see that instead of having a smaller weight on top, we have a larger weight of 4 kilograms on top of a 2 kilogram weight. And the question is, what forces is the 2 kilogram weight feeling? So we can see that there's always the gravitational force of the weight of the gravitational force that's acting on the object, and there's also a normal force from the surface, that's a contact force, and there's a second contact force, which is the contact force down from the 4 kilogram mass. We can put all of these together and see that because it's not, the 2 kilogram mass is not accelerating, then obviously all the forces balance. But the thing that's interesting about this is that even though the 4 kilogram weight has 2 kind of wings hanging off over the sides, it's still able to deliver all of its weight, which is twice the weight of the 2 kilogram mass, onto the 2 kilogram mass.